Welcome to Flictronics. This is a certified technology specialist course. In this video, we'll talk about audio systems, a key foundation for any AV professional. Here is what we'll cover in this video. We will talk about the basics of sound propagation. We will then talk about sound wave frequency and wavelength. We'll talk about concepts like harmonics, decibels, and the sound environment, and how these concepts apply to the audio signal chain from microphones to loudspeakers. We'll then move on to signal levels, cables, circuits in professional audio systems, and finally we'll close with an essential digital audio concepts including sampling, bit depth, and dynamic range. If you've watched my previous videos, you would have a basic understanding of sampling, bit depth, and bit rate. Stick around to the end for a couple of quizzes to test your understanding. To grasp audio systems fully, we start with how we hear sounds. Your ears capture sound waves, which are effectively compressions traveling through air. As sound travels through air, pushing back on air particles, those waves become mechanical vibrations in your ear, and then they transform into electrical signals interpreted by your brain as sound. This is briefly the signal flow, if you like, from sound interacting with air particles up until the point you hear it. Damage at any stage here can significantly affect your hearing. Now that we understand that sound travels as waves rippling, pushing back on air particles, let's dive a little bit deeper. As sound travels as compression through compressible media like air or water, we got to understand that it does not travel through a vacuum like space. For example, vibrations from a plucked guitar string or your vocal cords or even wind blowing cause these waves to ripple through the air. It's a classic example, but it's a really good way to understand how sound waves travel. Imagine dropping a rock into a pond. The ripples expanding outward are exactly like sound waves. They radiate in all directions as alternating compressions and refractions. This is exactly how sound waves behave into the air around you. Let's talk about acoustics a little bit so we can understand sound waves. Acoustics is the science that studies how sound behaves and how it interacts with the environment and how it is also perceived. Acoustics isn't just placing foam panels and absorbers on walls. It's a deeper understanding of how sound propagates, reflects, and interacts with the structure and the listeners. The field itself covers several fundamental topics: sound generation, how vibrations become audible waves; propagation, how sound waves travel through different media, air, water, concrete, and steel, for example; interaction with boundaries, how sound reflects, absorbs, or transmits through different material; design, how shape, size, and materials within spaces influence sound behavior; and perception, how your ears and brain interpret sound. When sound energy radiates outward, it eventually encounters surfaces. Think walls, ceilings, floors, furniture, even people. According to the law of conservation of energy, sound energy does not vanish. It either reflects, is absorbed, or transmits through boundaries. Reflection simply means that sound bounces off surfaces, continuing within the environment. Absorption, sound energy is converted into heat energy within materials, reducing the overall sound levels. Transmission means the sound passes through partitions or structural elements into adjacent spaces. Think poorly designed cinemas, for example. There are two primary types of reflection: direct and diffuse. Let's talk about direct first. This means that sound waves bounce off a smooth, hard surface, like a polished wall, at equal angles to how they arrived. And this is very similar to a mirror reflecting light. Diffuse reflection occurs when sound hits uneven or irregular surfaces. And when that happens, it scatters in many directions. This can help reduce unwanted echoes and evenly distribute sound throughout the space. This type of reflection depends on surface smoothness relative to the wavelength of the sound. Shorter wavelength, so higher frequency, behave very differently from longer wavelength. As a result, materials and structures in a room can influence how clear or muddled sound may be. Let's expand on those concepts a little bit. When sound repeatedly reflects off hard surfaces, it creates numerous overlapping reflections. This phenomenon is called reverberation. It is characterized by lingering, persistent sound. While moderate reverberation can enhance music, excessive amounts of it, which is common in large rooms with reflective surfaces, can reduce speech intelligibility and clarity. Typical small meeting rooms or conferencing rooms rarely exhibit true reverberation, but may have troublesome with short reflections. When materials differ in their capacity to absorb sound, porous absorbers, for example, rugs, carpets, acoustic ceiling tiles, or foam, or maybe furniture and even people, they convert sound energy into minor heat through friction with the air particles or molecules passing through their porous surface. This is called absorption. It's very important to remember that absorptive material usually only work effectively within a limited frequency range. Sound outside these frequencies will either be reflected or transmitted. And for sound that isn't absorbed or reflected, it will pass through the walls, the ceilings, the floors, or structural connections. It will enter adjacent spaces. Factors affecting transmission, including the mass, stiffness, structure, and design of partitions. This also includes any air gaps or weaknesses within the construction. One of the most valuable skills that you will have is understanding how to control ambient noise. Controlling ambient noise is crucial because excessive background noise can disrupt clear communications and reduce intelligibility. We define ambient noise as any sound within an environment that interferes with the desired audio, such as equipment fans, climate control systems, street noise, or conversations outside the room. An acoustician or an AV consultant typically specifies acceptable noise levels tailored to the room's purpose. For example, an auditorium will have stricter noise standards than a gymnasium. So, how do you manage acoustics? Managing acoustics is not only about reducing noise, it's about creating environments or treating environments and creating one that supports the intended use. Reflection control means positioning material or use angled surfaces to manage specular reflections. Another approach is diffusion, which employs uneven surfaces to scatter sound and create balanced coverage. Absorption is strategically placing absorptive material to reduce problematic echoes and reverberation. Transmission loss is the idea of constructing walls and partitions to limit sound traveling between rooms. Balancing these elements is the art and the science of acoustic treatment, ensuring audio clarity, comfort, and effectiveness in any environment. So, key takeaways from this is understanding that sound propagation involves reflection, absorption, and transmission. Surface and room geometry shape how sound behaves. Managing reflections and reverberation is vital for clarity and comfort. Controlling ambient noise ensures clear communication. And finally, good acoustic design supports the intended audio experience. Understanding these fundamentals of acoustics equips you to create environments where sound works harmoniously, enhancing comfort, intelligibility, and enjoyment and engagement for others. There are two key characteristics that define sound waves: frequency and wavelength. There are more characteristics that we are interested in, but let's start with the two key ones. Frequency is how many wave cycles happen per second. This is always measured in hertz or the multiplications. As we said, frequency is how many wave cycles happen per second. And the human hearing is typically from 20 hertz, think deep bass register, to 20,000 hertz, high treble register. We can say 20K. Now, in terms of wavelength, it is the physical distance from one wave cycle to the next identical point. Wavelength and frequency are directly related to the speed of sound, which is around 343 meters per second, or 1 foot per millisecond at room temperature. Let's take a couple of examples to understand what wavelength is. A 20 hertz wave will have the wavelength of about 17 meters, or 56 feet. Those will be long, deep waves. And for the highest point you can hear, which is 20K, as we said, has the wavelength of about 17 millimeters, so about 0.67 inches. That is short, sharp waves. So how do we structure or organize those frequencies from 20 hertz to 20K? We organize audio frequencies into bands. It's easier to remember those and easier to manage when you are processing audio. Those bands are often called octaves, each doubling in frequency. And this aligns with our ear's logarithmic sensitivity. Each octave doubling feels evenly spaced musically. For example, when you play notes, say A at 22 hertz, it naturally produces harmonics around it, upper harmonics and lower harmonics. Additional vibrations at multiplications of 22, like 440 hertz or 660 and beyond, are called upper harmonics. These harmonics shape each sound's unique character or timbre. Next, let's talk about the decibel scale and some real-world examples. You might want to ask yourself, so how do we measure loudness at this point? We use the decibel. Before we dive deeper into this, remember that decibel is a logarithmic unit comparing sound intensity to a reference point. So in and of itself, it's not an absolute measurement. It's a comparison between two values. So if we say 0 decibels is about the threshold of hearing, the faintest sound you can detect. Every increase of 10 means the sound's intensity grows 10 times stronger. So 10 dB is 10 times louder than 0 dB, according to your reference point. And 20 dB is 100 times louder, and so on. So for example, a whisper can be 30 dB, normal conversation can be about 60, a busy street can be about 80 or 90, a loud rock gig can be 110 or 120. And that would be the threshold of pain. Note that decibels do not represent absolute values. They express a ratio or comparison between two numbers. This means measurements are meaningful only when referenced to something else. For instance, saying a sound measure of 85 dB is incomplete without a reference. 85 dB of what? Sound pressure level, electrical power, voltage. The context matters greatly. Let's highlight some standard reference levels. To understand audio clearly, we typically use standard references. Sound pressure level is reference to the threshold of human hearing, i.e. 0 dB SPL, which is 20 micropascal, the quietest a human can hear. Voltage levels are measured in dBu or dBV. 0 dBu equals 0.775 volts. This is very common in professional audio. 0 dBV is 1.0 volts. That is the common one in consumer audio. Power levels are referenced as 0 dBm in reference to 1 milliwatt as the reference level. This makes comparing audio signals or power differences straightforward and consistent. You might also see negative dB values, such as minus 20 dBu. Negative doesn't mean the voltage itself is negative. It simply means the measured level is below the reference. For example, minus 20 dBu is less than 0 dBu, less than 0.775 volts, but still a positive voltage. Decibels align closely with human hearing perception. Here are some important things to take note of. 1 dB change is the smallest change humans can typically perceive, but only noticeable under careful listening conditions. 3 dB change is considered a just noticeable difference. For instance, increasing from 85 dB SPL to 88 is clearly noticeable, but subtle. 10 dB change, humans perceive that as twice as loud or half as loud. So going from 85 dB SPL to 95 sounds approximately twice as loud. And that's what it means by the dB being a logarithmic scale. Next, let's break down the inverse square law and its impact on audio. Since sound travels outward from its source like ripples expanding from a rock thrown in the water, unlike water, however, being confined to a specific plane, sound radiates in all directions, so it forms a sphere effectively. The intensity of sound follows the inverse square law. Every time you double your distance from a sound source, the sound pressure drops by approximately 6 dB. Conversely, if you move closer, halving your distance, sound pressure increases by about 6 dB. An example would explain this better. If you're standing 5 meters from a speaker at 90 dB SPL, moving to 10 meters away would drop the level to approximately 84 dB SPL. Moving from 10 meters back to 5 meters would increase sound pressure level by approximately 6 dB. Why does this work, and how does it work? This phenomenon occurs because each time the distance doubles, sound energy spreads out 4 times the area. At double the distance, the same amount of energy covers 4 times the surface area, causing each point on that surface to receive only 1/4 the original intensity. A quarter intensity translates into a 6 dB reduction. Just remember that there are practical considerations and limitations. In an ideal condition, free field environment, if you will, with no reflections from walls, ceilings, or floors, this 6 dB per doubling rule is precise. But real-world environments have surfaces reflecting sound, affecting how sound levels decrease with distance, as well as absorbers and much more. So in practice, expect variations depending on room material and geometry. Interestingly, the inverse square law isn't just for sounds. It applies to anything radiating from a point source, so light, radio waves, and even forces like magnetic fields. We will see the inverse square law again when we talk about video and light. So, key takeaways. Decibels measure relative changes always against a defined reference. Smallest noticeable difference equals 1 dB. For clearly noticeable, 3 dB. Perceived as twice or half as loud is 10 dB. Inverse square law, doubling distance decreases sound intensity by 6 dB. Halving distance increases by 6 dB. And finally, real environments alter these effects. Reflection surfaces matter. Now let's explore how we translate analog sounds into digital signals.
When sound hits the microphone, that sound energy is converted to electrical signals. And then it goes to a mixer and some processors to amplify, route, and enhance. And the amplifier then strengthens that signal and push it out to loudspeakers. This energy conversion, this process, acoustic to electric and back, is called transduction. So microphones and speakers are effectively transducers. Remember that most audio starts analog, continuous waves, but digital audio converts these into discrete numerical samples, capturing audio signals accurately and reliably. Analog audio is often described as rich but susceptible to noise distortion and degradation over time. Digital audio, on the other hand, is arguably clearer, stable, with higher achievable dynamic range. Digital audio quality then relies on two important parameters: sampling rate and bit depth. Sampling rate, or samples per second, often measured in hertz, to capture a frequency accurately, you must at least sample twice that frequency. This is called the Nyquist theorem. Legacy discs or CDs sample at 44.1K to cover the full human hearing spectrum, which ranges from 20 Hz to 20K. This is to avoid aliasing. Aliasing occurs when sampling too slowly. It causes high frequency signals to appear incorrectly as lower frequencies. The other important parameter is bit depth. Bit depth is how finely amplitude is measured at each sample. 16-bit audio gives 65,536 discrete amplitude steps, producing a dynamic range of about 96 dB. It's excellent for listening. 24-bit audio is common in professional environments. It provides about 144 dB of dynamic range. It offers more detail and less quantization noise. There is also 32-bit in some equipment and some gear that support it. 24-bit provides about 144 dB of dynamic range, more detail and less quantization noise. Audio signals are often transmitted and stored digitally, but digital audio files, especially uncompressed, can be very large. To save space and bandwidth, digital audio compression methods are used. There are two types of compression. Lossless audio compression reduces file size by about 50 to 70% without losing any audio information. The compressed audio, when decoded, is bit for bit identical to the original. Common lossless formats are FLAC, which is widely used for archiving and streaming, Apple Lossless, commonly used in Apple devices. Lossless audio provides perfect fidelity, but requires more processing power to compress and decompress. It's ideal when preserving original audio quality is essential. Lossy audio compression significantly reduces file sizes by discarding parts of the audio that human ears are less sensitive to, using psychoacoustic modeling. A common example is MP3, the most widely used lossy format. It can compress audio files by 75 to 90% compared to uncompressed CD quality audio. Another lossy format is AAC. It's used by streaming services, and it offers improved audio quality at lower bit rates compared to MP3. Lossy compression is effective where maximum storage efficiency or lower bandwidth is required. Think streaming music services, speech announcements, or audio in high noise environments.
When it comes to signal levels, audio signals operate at different ones. Mic levels, those are weak signals from microphones. They are often measured in millivolts. Professional line level is stronger, typically about 1 volt. And then, of course, you have speaker level. This is high-powered, tens of volts. It's required to drive loudspeakers. What you need to remember is that you must match and adjust these levels carefully to avoid noise and distortion. Gain structure and mismatching levels is the most common problem in the audio world. So how do we connect an audio system together? Quality of audio really depends on appropriate and proper connections. In the analog world, balanced circuits use shielded twisted pair cables. common XLR ones to cancel out noise for long runs. It's the standard for professional audio, whether you're using microphones or you are using outboard gear. Unbalanced circuits like RCA cables, 3.5 mil jacks. They are simpler, cheaper, and shorter cables, but are prone to noise and interference. You can see those commonly in consumer audio products. Once you've connected your audio system and you have some sound going from loudspeakers, so how do you avoid feedback? First of all, let's clearly define what feedback is. Feedback is a screeching or squeaking loop when a mic picks up its own amplified sound. And to avoid this, there are a few basic strategies that you gotta think about. You can place loudspeakers ahead of microphones, or you can use directional microphones, or you can minimize system gain just enough for amplification. There are other more involved strategies, but those are the basic ones. Let's cover a few common audio systems in AV. Sound reinforcement or PA systems, those are mainly for amplifying voice/music clearly to audiences. Think large gigs in arenas. Another common one is mix-minus systems. These are special setups avoiding feedback by carefully routing microphones and speakers. And this is common in broadcast environments, newsrooms, and communication systems. Intercom or paging systems, these are either two-way communication systems or one-way system for public announcements. Audio conferencing systems, these provide clarity for calls involving echo cancellation and onboard digital signal processing. And of course, for office environments, there's an honorable mention, which is sound masking systems. Those provide background noise that is added intentionally to improve speech privacy. To effectively select and utilize microphones, you need to understand their construction, operation, intended uses, and key performance characteristics such as type, sensitivity, frequency response, impedance, and directional capabilities. Let's dive into these details. Microphones transform acoustic sound energy into electrical signals. They vary widely in type, size, and internal construction. Although early telephones often used carbon microphones, today's pro audio applications commonly employ microphones like dynamics, condensers, electrets, and MEMS, or microelectrical mechanical systems. Each type has unique application and strengths. First up, the dynamic microphone. The dynamic microphone uses a simple, robust design consisting of a diaphragm connected to a wire coil. That coil is positioned within a permanent magnetic field. When sound waves strike through the diaphragm, it moves the attached coil through the magnetic field, generating a small electrical voltage proportional to the acoustic pressure. This electrical output is known as mic level signal, typically just a few millivolts. The advantage of using a dynamic microphone is that it's durable and reliable, economical, and can handle high sound pressure levels. It's ideal for vocals, drums, and loud instruments, and obviously no external power required. Next up is the condenser microphone. A condenser microphone functions based on electrical capacitance. Inside a condenser, there are two conductive plates separated by an insulating material, which is usually air. A condenser microphone consists of a thin conductive diaphragm and a conductive backplate positioned closely behind it. When the sound waves move the diaphragm, the distance between the diaphragm and the backplate changes, altering the capacitance and creating a small electrical voltage. Condenser microphones produce a much weaker signals than the dynamic ones. Therefore, it typically includes a built-in preamplifier powered via external means, such as phantom power or batteries. This allows the microphone to boost the output to a mic level. The advantages of using a condenser is that it has greater sensitivity and clarity, particularly at higher frequencies. It has a wide, uniform frequency response and it is excellent for capturing vocals, acoustic instruments, and studio recordings. Let's talk about electret microphones. An electret microphone is a specialized type of condenser microphone using a permanently charged material, the electric, and on either the diaphragm or the backplate. The permanent charge eliminates the need for a higher external voltage to polarize the capacitor. The advantages of such a microphone is that it's small and it's compact in size, and it requires minimal external power. A battery or standard phantom power would work, and it's common in wearables and portable devices such as lavaliers and headsets and consumer electronics as well. MEMS microphones, or micro electromechanical systems. These are very tiny microphones built directly onto silicon chips using semiconductor manufacturing techniques. MEMS microphones usually function as miniature condenser or piezoelectric microphones integrated directly with electronic circuits. The advantages of such a microphone is that it's extremely small in size, and it allows integration into compact electronic devices like smartphones, tablets, and wearables. Multiple microphones can be combined into arrays to enhance sensitivity and create steerable directional pickup patterns. And of course, the on-chip digital signal processing. It includes analog to digital conversion, and it enhances signal quality and versatility. This type of technology continues to grow today, particularly in conferencing systems, smart speakers, VR, and personal communications devices. So let's expand a little bit about phantom power. Phantom power is a method of providing electrical power remotely through audio cables to operate condensers and electret microphones. Standard phantom power ranges from 12 volts to 48 volts direct current, 48 volts being the most common in this case. It is applied equally to the two signal conductors of a balanced audio cable using the cable shield as a ground return. It doesn't affect the audio signal integrity and is completely safe for dynamic microphones, which simply ignores that voltage. Many audio mixing consoles include phantom power, often switchable per channel or across multiple channels. Standalone phantom power supply units are also available. So we talked about microphone electrical design. Let's talk about their physical design and placement. Microphones come in various configurations tailored to specific applications. So, for example, handheld microphones are designed for speech or vocal performances. They feature an internal shock mount to minimize handling noise. A boundary microphone, for example, is usually installed flush against tables, floors, or walls. Sound reflections from these surfaces enhance microphone pickup. Another common microphone type is the gooseneck. It's usually mounted on flexible stems, and it's frequently used on lecterns and conference tables. It's often paired with shock mounts for vibration isolation. A highly directional type of microphone is the shotgun. It is used extensively in film, video production, and field recordings. You can also find it being mounted on cameras, poles, or boom arms. There are some mics that are optimized for capturing tonal characteristics and dynamics of musical instruments. Those are simply called instrument microphones. Those are available in both dynamic and condenser designs. Lavalier and head-worn microphones. These are discrete microphones worn by presenters, actors, or broadcast professionals. They are often electric design, prioritizing appearance and minimal visual impact. The most popular in audio conferencing is the beamforming array microphone. Those are types of array microphones that are composed of multiple microphone elements, typically MEMS or condensers. They are combined electronically to create focused, steerable audio pickup. They are ideal for conferencing systems and large meeting spaces. The sensitivity of each microphone arriving in different direction is defined as the microphone polar pattern. It is crucial that you select the right mic for your application. Let's review a few polar patterns.
The first one we're going to mention is the omnidirectional. It captures sound equally from all directions.
The second one is the cardioid. It's very common, it's highly sensitive from the front, and it reduces sound from the sides and the rear. It's ideal for general vocal use. A couple of enhancements on the cardioid is the hyper and the super cardioid. The hyper one has narrower front sensitivity and better side rejection, but some rear sensitivity. It's really effective in noisy environments. The supercardioid is similar to the hyper one, but with even narrower sensitivity in the front and slightly more sensitivity directly behind. And finally, the bidirectional, which is also known as the figure of eight. It's equally sensitive front and back, with minimal sensitivity from the sides, and is usually used for face-to-face interviews or dual source recordings. Now let's cover sensitivity. Microphone sensitivity measures how effectively a microphone converts sounds into electrical energy. A higher sensitivity microphone outputs a stronger electrical signal for the same sound pressure level. Condenser microphones generally have higher sensitivity, which is beneficial for distant sources. Dynamic ones often have lower sensitivity, which is suitable for loud sources or close miking techniques. A microphone's ability to capture frequencies across the audible range is called the frequency response. And this is often depicted graphically, indicating the microphone's tonal characteristics. Directional microphones have optimal frequency response directly in front of them, becoming uneven or diminished as you move off axis. A key driver in reducing noise interference and allowing longer cable runs is the impedance of a microphone. This is measured in ohms, and it's the microphone's resistance to the alternating current flow. Microphone impedance must be compatible with the input device. Low impedance are usually rated at 200 ohms or less. These are professional microphones. Higher ones are above 25K, and these are usually consumer or older designs. The other types that we haven't talked about are wireless microphones. Wireless microphones transmit audio via radio frequency or infrared signals. It eliminates the need for cables. Some of those are handheld wireless microphones that integrate the transmitter in the mic handle. Other types have a body pack transmitter that connects to the lavalier or the headset microphone. Wireless microphone systems require careful frequency coordination or spectrum management to avoid interference from other wireless devices, broadcast signals, and local regulations. Digital wireless systems have emerged to enhance audio quality, privacy, and reliability. Though wireless connections inherently have more potential interference and reliability, digital wireless systems have emerged to enhance audio quality, privacy, and reliability. Just remember that wireless connections inherently have potential interference and reliability risks than their wired counterparts. So, key takeaways for us. Choose the microphone type and design based on your specific application and environment. Understand polar patterns to optimize sound capture and reduce unwanted noise. Select sensitivity and impedance matching your audio system for best performance, and consider wireless when mobility is essential. In an audio system, the sound captured by a microphone travels through several essential devices, each serving a unique role. So let's take a look at some of those. The first one we have is an audio mixer, often called a mixing console or a mixing desk. Think of this as the hub where multiple audio signals are combined, controlled, and routed. Mixers handle inputs from microphones, instruments, and playback devices, blending them into a cohesive sound mix. Mixers are described by their inputs and outputs, such as an 8x2 mixer. This means that it has 8 inputs and 2 outputs. Each channel has gain controls, equalization, and routing options. Some mixers have automatic mic channels using gating or gain sharing. Gated mixers switch channels on and off automatically, while gain sharing ones adjust channel levels dynamically. Remember, automatic mixers are great for speech, but music typically requires manual mixing. Next, we have dynamics. Dynamics often refer to compressors, limiters, and gates. Dynamics are audio processors that refine signals by adjusting their dynamic range, i.e., the difference between loud and quiet sounds. For example, a compressor reduces the level of loud sounds, smoothing out peaks and creating a balanced sound. A limiter is like an extreme compressor, prevents audio from exceeding a preset threshold, protecting speakers, for example, from damage. Expanders and gates do the opposite. They lower or mute quieter signals, reducing background noise. When it comes to filters, they are devices that remove unwanted frequency. A high-pass filter removes low frequencies, while a low-pass filter removes highs. A notch filter targets a specific problem frequency. Equalizers or EQs adjust the balance between frequency ranges. A graphic equalizer provides simple visual controls using sliders at fixed frequencies. A parametric equalizer is a more flexible one. It offers more control, letting you precisely adjust the frequency, bandwidth, also called Q, and gain. Delays align the timing of sound from multiple speakers. Imagine an auditorium where balcony speakers must be delayed slightly to match the main speakers, preventing echoes, for example. Delays synchronize these sound arrivals, creating clear audio coverage. Can be used for other things as well. DSPs, or digital signal processors, are versatile tools that digitally enhance audio signals. They combine functions like equalization, mixing, echo cancellation, feedback suppression, and more into a single device. DSPs can be built into mixing consoles, amplifiers, or used as standalone devices. Configuring a DSP typically involves using software or a web interface, making DSP programming skills valuable for AV professionals. At the end of our signal chain, just before loudspeakers, we have power amplifiers. Power amplifiers boosts audio signals from line level to loudspeaker level. This amplification drives loudspeakers with the right voltage and power, producing clear, powerful audio. Amplifiers vary greatly in power capacity, influencing loudspeaker selection and cable sizing. Professional loudspeakers commonly use robust connectors such as Speak-On. And finally, the loudspeaker. Loudspeakers are commonly multi-driver. They convert electrical signal back into sound waves. But because no single driver can reproduce all frequencies accurately, loudspeakers often use multiple drivers for different frequency ranges: tweeters for highs, mid-range drivers, and woofers for lows. A crossover divides the audio spectrum, sending each driver the frequencies it's best suited to reproduce. Crossovers can be passive, i.e., built into the speaker, or active, part of a DSP or amplifier system. When selecting loudspeakers, pay close attention to the specifications such as sensitivity, impedance, and frequency response. Sensitivity is measured in decibels at 1 watt from 1 meter, so dB SPL per watt at 1 meter. Shows how efficiently the speaker converts electrical energy to sound. Impedance is typically 4, 8, or 16 ohms. It affects compatibility with amplifiers. Knowing this prevents distortion and damage. And loudspeakers' frequency response shows which frequencies the speaker accurately reproduces, and polar plots show how sound spreads out from the speaker. It's important to monitor audio levels throughout your system to ensure clear, undistorted audio. Each stage from mixer to amplifier has meters or LED indicators. Check your levels carefully. Too low and your signal will become noisy. Too high and it will distort. Good practice is never to max out any individual gain stage. Proper gain staging or gain structure provides the best audio quality. In our industry today, audio is frequently transported digitally across Layer 3 IP networks. Several protocols are widely used for this. One is AES-67. It's an open standard that provides interoperability across different manufacturers' networked audio solutions. Another one is AVB. It's an IEEE standard protocol. It offers real-time transmission of uncompressed audio and video streams. It requires AVB certified network switches. It supports up to 200 channels of 48K and 24-bit audio. Dante is the widely adopted protocol by Audinate. It transmits audio over standard IP networks. This happens over a 1 gigabit Ethernet cable, and it supports up to 1024 audio channels at 48K 24-bit. It's highly scalable. It uses standard network switches without specialized hardware. We will expand on networked audio in future videos, but I would like to give an overview. Digital audio flows can be streamed or transmitted over networks using two methods. One is called unicast and one is called multicast. Unicast is a one-to-one transmission method. Each additional listener requires extra bandwidth. It's suitable for personalized streaming, like individual phone calls or direct streams. Multicast streaming is a one-to-many method. It uses Class D multicast IP addresses. Don't worry about that now. We're going to cover networks later. It efficiently uses bandwidth by sending one stream that multiple clients can subscribe or tune to simultaneously. It's ideal for enterprise-wide announcements or large group conferencing within a network. So when you think which one to choose, it's important to consider practical applications and considerations. When choosing audio compression and streaming methods, consider the required audio quality and the dynamic range, the available bandwidth and network infrastructure, and the processing latency introduced by encoding and decoding process. So, key takeaways. Sampling rate and bit depth determine digital audio quality. Uncompressed audio provides maximum quality but large file sizes. Lossless compression preserves audio fidelity. Lossy, on the other hand, greatly reduces file size but sacrifices quality. We covered networked audio protocols like Dante, AVB, AS67. Those simplify distribution and interoperability. Choosing unicast or multicast is always based on network needs and audience size. Understanding sample rates, bit depth, and audio compression ensures you effectively choose the best digital audio solution, balancing quality, efficiency, and practicality for your projects. In this video, you've learned everything from how sound moves through air, how we measure it, to the workings of microphones, consoles, amplifiers, and loudspeakers. Here are a few quizzes to test your understanding. What is the term for the movement of sound through air? Pause the video now to think about your answer. And the answer is A, propagation. Propagation is the term for the movement of sound through air. Quiz number 2. Wavelength refers to... Pause the video now to think about your answer. And the answer is C. Wavelength refers to the physical distance between two identical points in a wave cycle. Quiz number 3. Acoustics studies how sound is blank as well as it is blank and blank. Pause the video now to think about your answer. And the answer is produced, propagation, control. Acoustics studies how sound is produced as well as its propagation and control. Thanks for watching. I'll see you on the next one.